So, hello everyone. Well, hi. Welcome back to our sessions of Computational Bioengineering. And perhaps some very brief announcements first. So as you see, like we're filling up the background material. There is more and more links and shown up. If there is new background material that you did not watch yet, perhaps give it a quick check, even if it's just to say, oh, I know that already. That's completely fine, but just check it out and let us know what is missing, what you learned from it, and so on. Yeah. So we love feedback. Next thing we wanted to say is there is a new homework that is up here. So we are completely aware that an old homework is still running, so don't worry, you're not too late there, that's perfectly fine. But since this course was very well adapted for a new homework that we think is very cool, we thought to start a new homework, but this homework will actually last for 3 weeks, because there is, I don't know about back at you at home, but like in France there is a holiday, and of course we don't want you to work have to work in this holiday, so there will be 3 weeks for this last homework. Not last, for the next homework. It's not. I promise you, it's not the last. Okay, and that brings me back to the session. And today's session will be about logical gates. So this is kind of a central thing in this course for several reasons. Yeah. So up until now, we kind of learned all the things we have as basics that we need to really address biological design, right? And today we want to kind of a little bit apply that to the, we think, interesting case of logical gates, of building Boolean gates in cells. And yeah, we will go into this in detail. And you will also find that the homework and the future homeworks, and already, like it was already last homework and also this homework and so on, this will be more and more evolving with this project that we promised you, that you will build, for example, an inverter. Yeah? So it's going more in the direction, for example, you will check out that today the homework will be, and the problem session will be about NOR gates and inverters and how to build this and how to build compilers about this. And so the topic of the future homeworks will be actually to create such inverters in the living cell. And today we are going to look into what is actually such an inverter, a more complex gate. So let's start with the simplest of all gates. So that is actually looking like that, and this is just a standard symbol for an inverter. It's a super basic digital gate. It has a single input. It has a single output. Sometimes called in different ways, but often set as the inverted output here. And its logic is super simple. It just takes a 0 and outputs a 1. And it takes a 1 and outputs a 0 in a digital way. Yeah? Of course, how to implement this in silicon and so on, this is non-trivial, and how to parameterize this and so on, and what is this analog behavior is completely non-trivial. Yeah? We will not look at it in digital circuits, but we will look at it in the context of concentrations and species inside a cell. So we will define this. But we want to implement this in a living cell, let's say. Yeah? On purpose, I'm not talking too much about the inputs and outputs yet. Huh? So I keep that a little bit open and a little bit vague, and we will see also later why we do that. Huh? Okay, so yeah, this is if you check out the code, there is 2 very nice libraries that we can really recommend. So one is actually for drawing in Python such circuits. That works pretty well, and we use this in the course. Yeah, and another one, and you might need to install this, is actually for plotting DNA circuits, and we will use this also heavily later. Just install it as you already know. Yeah, here we see the inverter, and what does a genetic design look like? Yeah? I mean, you can already perhaps guess a genetic design from what we know about repression, right? So let's say this is our DNA, yeah, or symbolic DNA. So what do we need to get this done? Yeah? So first we need an output, right? So this is our output. Let's say we are going to use an output like GFP or something, a protein that we express. This will be our output, etc. Will be expressed here. Of course, whenever we express something, we need a terminator. Otherwise, we are just continuing here with our RNA polymerases, which is not a good news. Like, let's terminate this. And of course, we always need a ribosome binding site. This should be also already clear from the microbiology 101 that we uploaded. So this is essentially the thing that the ribosome will attach to when this is already transcribed to an mRNA. Yeah? So it's a start of translation, if you want to say so. Yeah? And then, of course, we need a promoter. Yeah? The symbol is like this. Yeah? We are using, by the way, this SBAR symbols here, and this plotting library that you will see in the code is also using this SBAR standard. It's a nice standard to draw such static circuits. Okay, but that's an always-on function. I mean, that produces just always one, like 100% set. We don't want that. We want to actually let it depend on some x. So let's say we have here some x. Same things as before. And let's, for simplicity, we just say we are always expressing that. And all we have to do now is actually to go from here and to repress that, right? Like, for example, now if x is high, so let's say we have this promoter here, yeah, then z will be low, and if x is low, then z will be high because it's not expressed. X is not expressed, and so this is not repressed, and the z is expressed. Yeah? So far so good. This should be almost clear from the introductory lecture, the lesson about repression, right? Like, everybody clear on that? Yeah? Okay. And so now the first question is, let's get a bit more systematic in this. So what is a gate here? Yeah, I mean, this is biological parts, but what are the gate boundaries here? And what is the inputs and outputs? So let's start to be not so vague, actually, like we were in the beginning. And I mean, we can actually say, for example, we already had this, right? We remember this formula, perhaps, where we had here the kind of, let's say, x here. This was the repressor, yeah? So we had this x, then binding to the promoter P, yeah? And this going back and forth in the bound state, yeah, and unbound state. And we had here the dissociation constant. So we say this is a super fast process. There is an equilibrium very fast. We don't want to care about the dynamics here. And we immediately got this, right, that we had x p divided by dx equals, what was that? So that was in the forward direction is a k plus. So we had a k plus here, and this is a k minus here. So we have to take that in this direction. This is a kd, if I'm right? I hope I got that right. I don't. I'm switching that back and forth. Okay, so but we have an equilibrium distribution here very quickly, and we can completely use that. Yeah? And especially we are interested in this is a repressed promoter, so we are actually interested in this one here, right? Yeah. Yeah, exactly. Yeah. Divided by the p total, for example. So how often is this in the unbound state divided by the p total? Yeah? Or if exactly. Yeah. And so the interesting part here is that we can. Oops. Hope that's okay. That we have here. We got here a transcription and translation rate. So this was a combined rate, right? So we can completely say now that our gate starts here and kind of stops here. Yeah. And I got you the formula here. Yeah. So this is the formula that you can see. So this is of course depending on x on the repressor. So we had this from this equilibrium. We had beta x is some beta max, and it's repressing. So it's a Hill function with only a 1 at the top, x divided by kd. Yeah. So and we easily check, for example, does this fulfill, by the way, all properties of this inverter? So for example, if we go with x, if we set this equal to 0, then we have just a 1 divided by 1 and we output beta max, yeah? Which is very nice because this is a beta max is exactly our high, our logical high, so that's perfectly fine. And be careful, we cannot just say this is 1 for the inverter, yeah? This doesn't make sense. Here, our logic has actually to go to, we have to say that this is very high, so we let it go to infinity, yeah? And if we do that, wait a second, I'm missing. Yeah, no, all is right. And it goes to 0. The complete stuff goes to 0, which is also perfectly fine with the inverter. So we completely get back our inverter as we want. Yeah? So everything is fine with this encapsulation in terms of to have an inverter. Yeah? So that's perfectly fine. All right. Okay. Are there any problems with this kind of gate formulation? I mean, now we have a digital design. We have a gate, right? It's an inverter. It has the properties of inverter. Any kind of problems that we might encounter? Like think of in the direction of, imagine you want to compose these inverters. Huh? You want to have a chain of inverters. You want an inverter right after again. Huh? So is this a very good idea to have as an input the concentration of a repressor and as an output the expression rate? Huh? Yeah? Yeah, exactly. I see nodding heads. So no, it's a very bad idea, or it's not a. Let's say it's a not very good idea. Yeah? And why is it a not? Because how do you want to compose that? I mean, you have two different units interfacing. Yeah, that's not very convenient. Of course, you can say, I mean, no problem. I can just translate this for the next gate. Yeah, and you can totally do that. Yeah, you would have to introduce a degradation rate, and then compute from a degradation rate, again the next concentration, and so on and so on. Yeah? You can totally do that, but there is actually a much nicer boxing of a gate that we want to present you, yeah, and that is actually used. So this is not so much used as a gate, and for the reasons of these mismatching unit systems. Yeah? And we'll show you this in a second. Yeah, no. Before I show you anything else, this is, by the way, the transfer characteristics of this inverter. So what is the transfer characteristics? This is just plotting here the X concentration and here the output, the set rate. So this is how it looks like. And of course, yeah, here, does it look like an inverter? I mean, those of you who have seen digital inverters, doesn't look very much like a digital inverter. Yeah? From a digital inverter, normally what you expect to see is something, you have here the input and here the output, right? And you want for a low input, you want a high output. So you want to start off here, then you want to end here, because if you have a high input, you want a low output, and then you have to somehow connect this. And how do you want to connect this? Any ideas how this should be connected? This kind of two plateaus here and here. Like what would be a good connection? What is perhaps not so favorable connection? Any ideas on what we would wish for if it would be perfect? Let's say, right? Yeah, what we want is actually a very high amplification in the middle. Like we want to amplify in the middle, away from the middle. So the perfect inverter would look like that. Just a step function at some threshold, probably in the middle, to be very symmetric and to keep space for noise on both sides. Of course, yeah, reality is not as perfect. So you will kind of have an S shape here. But we would like this S shape to be very steep, yeah, because we want really high amplification. If for some reason our input is not perfectly here, yeah, but it's a little bit to the side here because of some Gaussian noise, or I don't know, or some chittering, some thermal noise or something, yeah. We really want to be amplified like we want to treat these almost the same, these two values, yeah. So we need an amplification that's amplifying away from the middle, from the symmetry point here in the middle. Huh? Exactly, so we are expecting such a curve. This is what we get. Doesn't look very nice, but it's okay. We will see in a second why it's okay. Yeah? And here we just play it, by the way, with Hill coefficients. Yeah? You can totally add here Hill coefficients. Yeah? And we didn't derive this in the lecture, but there's different reasons for higher order, like bigger than n Hill coefficients here. Things being, for example, cooperativity and some internal state and so happening. Yeah. And this is just testing, for example, with a Hill coefficient of 2, yeah, which is totally possible, for example. Yeah. So you see, this is steeper with a steeper Hill coefficient, yeah, with a higher Hill coefficient, but you still see they're quite the same, right? Yeah. Hey, can I help you? Okay. And so let's look a bit. Let's zoom a bit in, because these gates have to deal with high concentration differences at the input, right? So this is why perhaps we got these things. So if we have very high concentrations and we want to see this variable and this variable, what you typically do is like you just log plot it. Yeah. So we just go to log plots, and here we are. And this looks much more nicely than this digital curves that we used from chip design, right? Again, it's you can say, okay, it's a bit cheating because we have a log plot and now we're happy. We just replot it, but this is very typical for these genetic designs that you don't want to distinguish so much. It's perhaps a big distinction to have between 0 and 10 molecules, but it's not so huge distinction whether you have now 20 or 100 molecules, right? So log plots is not a so unfair way to look at characteristics, in fact. So this is pretty fine. But of course, you have to check whether the system works in the end. Okay, but looks good. Still, we are not happy about interfacing. And if one thing is important in digital design, then it's really interfacing. So we can't do that here. We cannot stick together gates here. It's a totally different x-axis unit than a y-axis unit. This is a concentration and this is a rate. Cannot stick that together. Okay. Let's look at a different boxing. And this is actually shown here. Again, these plots have been obtained with this nice library. Really cool thing to check out there if you want to plot for your papers or something, DNA circuits. Okay, let's box that in this way. So we are actually splitting that here. Remove that too. Right. So we are stopping it here, kind of. I will say in a second why I make 2 boxes and not 1, but of course for the moment we can just have also 1 box. That's completely fine. And I'm going to move this thing here just to make the box nicely cut. And here we are. This is now all this kind of shaded area here is kind of our gate, yeah. And for the moment they can be completely connected. There is no problem with that, of hiding X completely inside them. What is now possible inputs and outputs? I mean, let's go for the output first, right? I mean, before we had this rate here, this expression rate beta here, yeah, that is not too different actually from a certain rate here, yeah, of RNA polymerases being active going in this direction here. For example, a potential unit could be RNA polymerases per second. Yeah, I don't know, just some activity of transcription you want here. Yeah? Right, because in the end, what is happening is actually the RNA polymerase is attaching here, initiating here transcription, and then moving to the right. And they are doing this with a certain rate. And this rate depends, of course, on the promoter, on the repressor, and so on and so on. Yeah? So we can totally say this is our output. That is roughly, of course, related to this rate beta here. But beta was a bit a lump sum of transcription, translation, and other things happening. Perhaps RNA polymerases are falling off here. Perhaps it doesn't include the ribosome bonding site. So perhaps the ribosome bonding site, depending on what type it is, it's attracting more ribosomes or less ribosomes and so on. So we don't do this, we just move the rate, but we keep this a rate, but we just move it to the transcription rate here. Or the promoter activity rate here. Yeah? And so if we want composability, why not do the same here? Yeah? We also have here a rate. And again, this will be RNA polymerases per second. In fact, people use not this absolute quantity, just because, for two reasons. Because first, it's super difficult to measure. Yeah? Not every lab can easily measure that. And the second thing being, this is very sensitive to environmental design, so the medium, the temperature, and whatnot, yeah, and all the things that are in your experiment. So it can vary hugely. So people normally normalize this to a normal design. So they take a promoter for example, on the same plasmid somewhere, and this is now by definition 1. Yeah? And then you say this is 1.5 being 1.5 more RNA polymerases per second than the others. Yeah? And there is a nice paper about this, that this is much more measurable and resistant to noise and so on in a large range. Yeah? But I write here the absolute unit, but keep in mind that this is often something like, which is called this relative promoter units, for example. Yeah? But actually anything that works as a promoter activity works here. Yeah? That's the important thing. Okay, so why? Okay, like I think you can be convinced that this thing here again works as an inverter if we encapsulate it like this with this input and output. I mean, it kind of was just a frame shift in the view, yeah. That works totally. And what is interesting is that the formula for this is also actually this Hill function. So it will be this formula that you see here, right? So it will be, let's say this is the output, that of x. We are just reformulating a little bit, and I will say this in a second. Why? With KD, and we are using already here the Hill coefficient n to be generic. So again, this was just a frame shift, and so this is an x. So very nicely. And we have just added this leakiness that we know also from the first lecture, right? Because if it's off, it's not a 0. It's probably some minimum rate here. Yeah? And if it's on, just not to have here something in addition, but really to have set max, yeah, that we get from the experiments. This is why we write this difference here on the top. I mean, this is just, and of course now you can nicely see the limits, right? If you put in a 0, then that should be a set max, which it is, right? And if you go with x to infinity again, or very high values, of course, then this drops to 0, and we have to recuperate the set min. So everything is fine. It's a nice inverter as before. Okay, and now this design is really the use design. This is how it's used. Nicely composable, nice features, everything works here. Yeah? So why did we paint these 2 boxes instead of 1 box? Any ideas?
One box is input.
Yeah. Exactly. So I just repeated for those who are on online. Like one is the input box and one is the output box, yeah? And they are completely disjoint. You can move them up, not up, but you can move them far away. There is no problem because they're connected by this X wiring signal X here, concentration, and you can place whatever you want in between. I mean, there is, of course, constraints from the genetic designs that you can do, but in principle, here at this level, you can place whatever you want in between. Okay. Okay. So what do you need me to give for such a gate, right? So first, you need some parameters if I give you such a gate. Yeah? So first, what are the components of this gate? Yeah. So I mean, we have just to count what is in these boxes, right? So we have a ribosome binding site, we have a repressor gene, we have a terminator in the inbox, and then we have a promoter that is related to this repressor. Yeah? So I have a fitting promoter on the outbox, and that's all the components. That's the gate components. Yeah? So it's written like this. Yeah? So this is the reason why it's written like the promoter at the end of this gate, because it's boxed like this. Huh? The second thing, you need to give me parameters, or you need to determine these parameters from experiment. So we have setmin, we have setmax, we have the Hill coefficient end, and we have KD. Yeah? And that's it. After you have this, you can just go ahead. Yeah? Okay. Let's get more complex. What happens if you want to build a NOR gate? So what is a NOR gate? Looks like this, right? This is the symbol of it. And it's just an OR gate with a negation in the end. Yeah? I mean, okay. Looks like this. Here is the symbol. What can we do as a genetic design to do that? And I start with a NOR gate that is perhaps not so heavily used, but is the most natural extension of this inverter. And this is I will not paint that because for the time, but I will show it to you in the slides. And you have that, of course, in the Jupyter notebook. Looks like that. I mean, that looks very familiar, right? This was the NOT gate from here. And what we have just added is we have just added a second input box. We kind of copied it, actually. I mean, in genetic design, there's reasons why you should really not copy it, because of recombination events between these two things. They could just recombine. But what is typically used, if you really use it, is like to vary a bit the sequence of this second thing. So it's not a bitwise copy, but it's a variation of a copy. But essentially, for us, mathematically, it's a copy. And now, so what does this thing have? It has now two inputs, right? This box has an input and this box has an input. And what's the formula? I mean, I have just deleted that formula, but so we have just to take essentially, let me write that like before, like here the inverter, and I call this now I for a reason. That was set min plus set max minus set min, right? Divided 1 plus I divided by KD to the power n. And so what is I? That was our inverter. This is just now the kind of the combined inputs. Yeah? For example, it's just x plus y. So we can totally just substitute that here and make that an 2 input gate. And you can figure out, so why can we add that? So the essential idea is actually that we are using RNA polymerases from this side and RNA polymerases from this side to actually have a combined, like it's assuming an additive effect. Yeah? This is not perhaps totally true, but since the concentrations here add really up, this is really additive. almost additive because they're of course stealing ribosomes and so on from a common pool, but roughly additive. This makes total sense and is a very nice approximation to this gate. And this gate is called split gate. You can think of it being the inputs being split up. You can again place whatever you want in between. Yeah, let's perhaps very quickly check out the limits. So are the limits okay? So what happens if you go with, I mean, you immediately see, right, if we go with x to infinity, or if we go with y to infinity, or if we go with x and y both to infinity, it's all the same because of the plus. So there is no distinction. Yeah? So essentially, every time you use an x, y, or both high, like infinity, you are going with this term to 0, and you're ending up with set min, which is actually a 0. So that's perfectly fine with the NOR. And on the other side, if you make both 0, then you end up with a set max, which is also completely fine. So it's a NOR gate. Okay. This is the table. This is what we just verified. And this is the transfer function. Now we have to go two-dimensional, of course, because we have two inputs. And this is how it looks like. Right? So we nicely see if it's 0, 0, it's high, and everything else it falls down to 0, right? And it's very symmetric because we're just adding up x and y. And because it's so symmetric in the end, what most people do is like they don't plot this two-dimensional plot here, but you're totally fine to plot just the one-dimensional plot. You can just plot the x plus in terms of x plus y of the combined activity. Yeah? So essentially, you plot the inverter logic. There is a second design that I want to talk about, and this is much more commonly used. Let me keep that here for a second for a reason. Yeah, and this design looks like that. Right? So this is called a tandem gate. Looks much simpler. It's also not anymore duplicated inputs. So what we have done here is actually we have put the promoters in tandem. They're not kind of in parallel, but kind of in sequence. Right? And this is where we spare the common parts of the ribosome and the expression gene. Yeah. Yeah, so I won't go into much detail here. The only thing is, do you see what happens now? Like, what happens in combination, how we have to combine these two inputs? And any ideas on this? Like, let's say like this promoter alone has a certain input rate. This promoter alone has a certain input rate. So what's kind of the combined input rate? Because once we have the combined input rate, we are done. This is just an inverter. Yeah, we have just our Hill function. We are completely done. So the difficulty is actually to get from this input rates the combined rate. And any ideas on how you would do that? First, very simple. What's your first shot? Not thinking. Yeah, we add them. Very good. Yes. And you made it. Like people do that. Totally. It's a linear combination. Of course, now that we think about it, there is some caveats to that, right? It's not completely correct but this depends now on the mechanistics. So why? Because, for example, we know that, for example, if this is being repressed, this is often because a repressor is sitting and blocking the RNA polymerases. And if something is sitting and blocking here, that's not a good thing for this rate. That's going to influence this rate. So this is not going to get through very nicely. So we can not completely linearly add them. So the second best shot was, let's use a factor here, let's say 0.3 or something, to say whatever rate comes out of this is being diminished, and then add it up with this. So it's a weighted sum. Again, if we think this is wait a second, this is not completely what's happening, because the state, if this is like the probability of this being blocked, depends on actually its input signal. Something that we don't have access to here in this gate. it's something from a previous gate. Because it was the Y that's going to block that. So depending if we had a lot of Y or a few Y, this is going to be more blocked or less blocked, or less blocking the X. And this is the third best thing people have come up with, is actually to have a formula. And surprisingly, it's a Hill formula, a bit more complex Hill formula, to incorporate a dynamic blocking factor. So the first thing is called static blocking factor, or static tandem blocking factor. If you just say, okay, that's just 0.3 times this input plus the other input. And if you make this depending on the Y concentration, the blocking of X, then it's a dynamic. And this dynamics this is used, for example, in the Cello 2 tool suite that you will check out in the problem session. One thing to say about the blocking. So there is two things, right? It's always this guy is blocking this one here. So normally the blocking is assumed only from here, affecting this one, and it's going to depend on something that is not part of the gate. So we have to be careful when forward propagating this information in the simulation of the circuit. Last thing to say here, this assumption that whatever is blocking here can influence this, but whatever is binding here, repressor binding here, is not influencing this. This has to do with the underlying mechanistics. Because if we think, for example, that this promoter is very close, and this thing here also kind of blocks this thing here, then we would have also account for that. But the assumption here is that this is far enough that any blocking happening here is not affecting this one. But you have to look at the mechanistics, whether this is really the case, whether you can do that or not. Okay. Here I don't write this on the board, but here you see actually the first shot we had at it, the linear income combination. Here exactly that was the linear, and this is the second best shot, is actually to have a tandem factor depending on the Y incorporated into the X to get the combined activity of the promoter. Right, and this is exactly what was proposed here and what is discussed here and used in Cello 2. And this is the way how to compute this tandem factor. You see here that this is kind of a Hill type function, and here there is this combined, and this tandem factor is used actually. It's not the tandem factor here. This is of Y. This is for Z. So this is the one that is handed over to the next gate that is using Z as a promoter, as an input promoter. So this is propagated forward also to the gate, to the next gate, to the downstream gate. And then in the end, just what we already completely know, the inverter characteristics is just used in terms of the combined input current, or the combined input promoter activity. Here I just want to show you a dynamic tandem blocking factor, how that typically looks like, right? So what we observe from the formulas here is actually like when we have such a formula, the first thing to know is what is its limits. What is it doing at 0 and what is it doing at infinity? And we easily verify like that this is actually getting alpha and alpha times beta in both cases, right? And typically, I mean, both are normally chosen between 0 and 1. And for example, if you're using a dynamic one, you start, for example, with an alpha of 1. So there is actually no blocking in this case, right? If there is no activity, and the more promoter activity you have from the previous gate, the less your factor will, the more blocking it will do. So remember, this factor is being multiplied to the activity, input activity, and you end up with alpha times beta. So here I choose beta 0.3 and alpha 1, so we have just 1 times 0.3, 0.3, and it nicely goes down like in a hill type function. So. All right. This finishes the part of the NOT gate and the NOR gate. And we will next go to so the NOT and the NOR gate. This was mostly to capture what people build when they construct genetic circuits. For example, this cello 1 and cello 2 sites are using that, and of course many other researchers in SynBio use that. The feed-forward loop, of course, you can build that totally, yeah. But this is also a structure that is very interestingly found in many regulation circuitry of existing wild-type bacteria. So we also decided to cover that here. Nothing prevents you of building an FFL if you need it, and it has some fun properties. We will see this in a second. So what is an FFL? So yeah, it's called a feed-forward loop, and it's not a loop. It's actually it's a directed graph that is splitting and merging again, but it's not a loop. And typically, like in terms of regulation, you have an input X to this FFL, yeah. Then this is split up, right? And here you have an output Z. Yeah, well, let's make this as two different inputs for a reason we will see in a second. And you have some here intermediate Y, and here we are just directly connecting. So yeah, so this is a kind of an FFL circuit. And now we have to specify this, what this means, because this is completely underspecified. We have to specify a few things. I'm not talking of the dynamics, of course, this is another thing, but I'm talking about just what do you do is errors mean. And this error here means, like, we draw a normal error when we mean activation. For example, some X activates a Y, and here and Y activates a Z and so on. And whenever we would mean suppression, we would just draw this arrow like just the same as before. And we start here with this simple X activates Y, Y activates Z, and X directly activates also Z. So now you can just do the puzzle of combine all different combinations, and you see here a nice picture of them. That looks like that. They can be classified in two big classes for also a nice reason. So there's the coherent class and the incoherent class, and the only difference between them being is actually you go the direct path and the indirect path, and you look if the combined action is consistent. For example, both activating, both inhibiting, then it's called coherent. Or if it's incoherent, inconsistent, one activating, the other suppressing. I'm not going into. We'll not go through the list, but this is the concept. There has been interesting studies about, again, what Thomas already talked about in the last time. Like, people look at what is most often found in wild type bacteria, and the answer here is like this one and this one. Not go into details here again, but this is like probably for a good reason. But this is the most found, and we will actually look at an example. Actually, we will look at an example from this and this afterwards, to see why they are used, or one example use, and not why they are used. We have to specify another thing, right? We have to specify what does it mean here. What's the logic here? Two activating things, because whenever you have two inputs, it's not clear. For example, imagine one is activating and the other is inhibiting. Who wins? or both activating, perhaps it's a bit more clear, but with both activating, for example, the question would be, let's imagine this is a logical 1, this is a logical 0, like logical here meaning like a high and a low concentration. So what's going to happen with Z? Is this sufficient to push Z over to activate Z? Or do we want both actually ones to push Z over the hill? Yeah? And essentially what you have to specify here is whether you are meaning an or an and. Right? Like the kind of the threshold that you need there. And yeah, exactly. And of course, like it could be that you have here deactivating, for example, then that would be an not Y, I don't know, let's choose or X, right? For example, yeah, I don't know, in this particular case. Yeah. And again, you can permute all the different combinations. Okay. Yes, let's go through that. This is perhaps something I let you read because it takes a bit more time. But when we want to, this we know how to model, right? I mean, it's just repression. So there is no big thing here. The big thing that is the modeling question here is actually how to model this, right? Yeah. So again, you have two inputs. Here again, we have concentrations, yeah? And here you want an output concentration set. And this is kind of a two-input gate. And we have seen the example of this NOR gate before, so we can totally do that. But is there a systematic way how to get, for example, something for this, a Hill function for this? Also, I spoiled a bit. It's again Hill functions all the way, yeah. But like, how to get that systematically, right? And there is a very nice technique. I mean, okay, first you can just write down the equilibrium equations and just solve them, one after the other. Yeah? But there's a very fast, quick approximation, not completely exact because it's doing the approximation we did also for the Hill function. Yeah? But it's very, very fast, and it comes from statistical physics. Yeah? So essentially, what we are going to find is actually all you classify in states. You classify when Z is being expressed in which states of its promoters, and what are the total states. And for each state, you would have to find a probability. It turns out that this probability is very difficult to find, or not so nice to find, because it depends again on some other states. But they are all relative to a certain state abundance. You can find all these probabilities. And this is called statistical weights. And since it's relative to the same thing at the top and relative to the same thing at the bottom, it just cancels out. And you have very quickly your Hill function. And we did that for you in the lecture. Not going to show it here, but this is, for example, one of the states of the statistical weights looks like that. For the end version, it would look like that. The total is that one. That is, of course, nicely written like that. And then immediately, plop, you have this for the end. So it's super fast just to get approximations very, very quickly. You get the same for the OR, you get the same for all the different things. And here we plotted these transfer functions. For example, for the N, it's plotted like this. For the OR, it's plotted like this. Very interesting, because that's not what we had for the NOR before, right? You remember our NOR was not looking so nicely. It was like all these symmetries, and this has to do with what we consider active here. Like we use a different activation assumption here, right? So we use much more the mechanistic model where we have this promoter, we have here a binding site for Y and here a binding site for X that is inhibiting. Yeah, and they are not completely independent, as I said. So this is when I said it's very important what is your mechanistic underlying model. Whether this affects, this blocks this and this blocks this, or only one blocks the other. Yeah? Yeah? And in the sum, where we just had the sum, we were saying, no, they are not at all blocking each other. They're completely, let's say, much more looking like that. Yeah? They're completely independent and far from each other. So this is why we have here a different function. Yeah? But you can completely recuperate also our function in case you use these different states here. Right? Yeah, this model even allows you to give you, I don't know, and not or not and what's not. Like you can immediately get all these functions. And the nice thing is, if you check out the limits, they're all correct, of course. Otherwise, we would do something wrong. Everything works here. This is logic, how it looks, transfer functions for something being inhibited in the underactivating, for example. Yeah. I mean, all depends on the parameters, but just to give you the kind of the look and feel of these functions. And once we have done the model for this, of course, now it's a simple thing to simulate it. It's just integrating, right? I mean, we have differential equations now, so we just give it an integrator in Python. We did this for you here. And this is some nice code. This is code, for example, that we have taken from the original lecture. So we did not only minor modifications to this code. So that was, just took that over. And here we solved that. Well, yeah. And I want to go to the circuit. Yeah, and here what was done is actually to simulate this particular circuit, right? So this was actually the thing where X activates Y, Y activates Z, and X directly activates Z. So everything is positive, no inhibition. And we have an AND logic here. And I have just been drawing this just drawing this as a circuit, yeah, because it immediately tells us like what's going on here. And what's going on here, like why would somebody do a circuit like this? I mean, it's just connecting essentially. I mean, if you say this is an identity, right? We can remove that logically. It does nothing. Just and then somebody splitting up the input and putting it to the same AND gate. That doesn't sound very purposeful, right? But it has a purpose, or it can have a purpose. And the purpose in it is in its delay, in its timing, right? So this path here will take longer than this path because it has the identity inside. Yeah? And what's that thing doing? Yeah. So actually, it's doing some things. Yeah. So if you think like, yeah, I think I show you simulations. Then it's nicer. Yeah? But you can think of any input there that's coming in here, any transition. For example, a falling transition that's coming in here. Yeah? Will be delayed here and will arrive first here. Yeah? So this will be still in its initial state when this arrives here, and only later this arrives here. Yeah? And you can do fun things with this. You can do, for example, after normalization, you get something like this. Yeah. So here the input X was plotted, which is just a step, like an up step and a down step, like an initial up step and down step. And then the output set is called. And what you see is here actually there is a so-called sign-sensitive delay. Initially we have a delay with respect to the input, and here we have less delay. Yeah? So we can do things like this. Yeah? So turning on takes time. Turning off is almost immediately. Yeah? Yeah, here is some studies like how big is this delay? There is just a sweep running, like to plot the delay function in terms of some properties of the system. So it shows that actually you can change that within some bounds. Yeah, this delay. And another property that this thing can do is actually to not only do a delay for the turning on, but to completely filter small pulses in the beginning. Yeah? if something, for example, if you can imagine, of course, if something has a delay being turned on, yeah, if you make it active and inactivate it immediately to take back the input before it's turned on, then this thing here would not turn on at all. Yeah? So it kind of has a resistance of being turned on and immediately goes off. Yeah? Yeah? So why would you use that as a cell? Any ideas?
For control?
Yeah, so definitely for control, yeah. But what's a task that you're very reluctant to do that, but you stop it immediately if somebody tells you, no, it's over? It's some let's say some heavy work, or like if you would have to go in with a lot of energy, like a lot of resources to do some really heavy lifting work. If somebody tells you, can you please do that for me? And like 10 seconds later says, oh no, sorry, it's already solved. Yeah, you are happy that you didn't start that, perhaps. Yeah, so it's perhaps something where you want to be really sure that this input is really needing that. Yeah? So and then only you go in with that. And this is actually how this is used in cells. So here is some. I'll let you read that. But there is some natural circuits in wild type bacteria that look like that. That are this FFL, like here. And this has been really experimentally observed of actually the step on taking delay and the step off being immediately, essentially. Yeah. So this is exactly when, for example, you want to be really sure to switch the metabolic circuit. For example, if you want to if some nutrients is missing, or you want to be really sure to assemble your motor as an E. coli, yeah? Before you really do that and so on. Like whenever like you have a big investment, you want to be really sure. Yeah, and there is, you can totally, of course, by switching just some knots in here in this circuit, you can totally do that, of course, in the other direction. You start it immediately, but you are reluctant to switch it off. Of course, same here, just symmetric. And I promised you another example. So this was the first very abundant FFL that we saw, the coherent one. And then there is the incoherent one, FFL, that is very abundant. And what can this one do? If we draw it as a circuit, it looks like that. I mean, we can move this bubble right here, right? So we have instead of the buffer, we now have like an inverter here in the path. And a nice property of this is actually, again, this is coming after this signal. This signal is very quickly shooting here, and then after some time, this negated signal arrives here. Yeah? So this is creating a pulse. Yeah? This is if you want to. Looks like this, right? You have an input signal that is a step, and your output signal set is here a pulse. Yeah? And of course, you can think also of several possibilities where it's very nice, like to. Let's say some input change happens and you just want to trigger an action. Yeah. And this is doing that. Okay, that brings me to the end of the lecture, and I think we are also well in time. Any questions? Like either from here or online? If it's online, feel free to post it and we read it. Yeah. So if there are no questions, feel free always, like always, feel free to ask questions. If you're watching this video later, just post in the Discord. Feel free to actively participate in the Discord. The Discord server is actually living with you, so you are the players in the Discord server. Yeah? So feel free to get the maximum out of us and out of your peers. There's very cool peers on it, so trigger us. And otherwise, I wish you fun in the problem session. So the problem session is going to apply this. It will be much more applied to genetic circuits. And what we will actually do is we will check out a very cool project. This is the Cello 2 that I was already mentioning here, yeah, and looking into how they build gates and yeah, checking out the characteristics, simulating. And the homework will be an extension of this. In the homework, the top part of the homework will be you will build your own compiler, yeah? Your own genetic compiler. Yeah. Okay, but don't worry. It's not like it's not a fully fledged compiler. It's pretty nice though. Yeah. So have fun. Yeah. Okay, that's it. Yeah. Thank you very much. Yeah.